In this tutorial, we're going to cover hash functions, hash tables, and Bloom filters. What is a hash function? Well, to answer this question, we're going to write our very own hash function. Let's suppose that we have a string, Python. The built-in ORD function takes in a single Unicode character as an argument and returns a number representing the Unicode code point of that character. So taking our word Python, if we do ORD uppercase P, we get 80. Note that this is different to passing in a lowercase p, which would give us 112. So our function takes in the word that we want to hash, creates an empty list, and then we loop through each character, passing the character into ORD to get the code point, and then appending that code point to our list. Finally, we return the sum of all the code points in the list, modulo 100. Now note that this is one particular example of a hash function. They don't all need to work that way, and in fact they don't. What makes this function useful? Well, whatever sequence of characters you pass into it, you're guaranteed to be returned a value that's between 0 and 99. Furthermore, the output for a given string will always be the same. And even though there are multiple inputs that will produce the same output, given the output, it's impossible to determine what the input was. So we can define a hash function as any algorithm that maps data of arbitrary length to data of a fixed length, i.e., whatever sort of data you put in, you always get a variable back within a certain range. So now that we're clear on hash functions, what about hash tables? A hash table is a data structure, and we can use the results of the hash function to determine the location in memory in which to store our data. So in this data structure, we have keys and we have values. And keys and values are a concept that you find all over the programming world. Let's take a block of memory with 100 elements, ranging from 0 to 99. We want to store the value London against the key city. So we run Python's built-in hash function on the key and mod by the size of our array, 100. That gives us the index. And then we can store our value at the location pointed to by the index. These are hash tables in their most basic form. Of course, you can already see the problem that will arise as the array becomes fuller and fuller. The likelihood that we'll have a hash value point to a spot in the array that's already taken increases. This is called a collision. And at this point, there are various things that we can do to find some free space. One strategy is linear probing. In this strategy, we look to the next available free space in the array. Or we can route a linked list at the index, and then we can store an arbitrary number of items in the linked list. Instead of a linked list, we can have a tree. When you have a data structure such as a linked list or a tree at every position in the array, this then becomes a chained hash table. If we do create a chained hash table though, we need to store the key with the value, otherwise we wouldn't know if we're retrieving the right thing. But it's easy for a table to start to perform poorly, and we can't have lookups that take all day. In terms of the code complexity of these operations, in terms of the big O notation, inserts, deletes and lookups take linear time. They're O1, whereas a linear search through a hash table has ON code complexity. Bloom filters are fast and space efficient and are used to test for membership in a set. So it can tell you if something is in a set, but it doesn't have the actual item itself for retrieval. So let's say we had a Bloom filter representing programming languages. It would tell us that Java and C++ are probably programming languages, and that a laptop is definitely not. But we can't use the Bloom filter to give us a list of all the programming languages that we use to populate it. Let's say we're put in charge of running Facebook for a day, and we have a problem with some users posting photos that go against our acceptable usage policy. Now, user A uploads a photo. How can we tell by looking at the uploaded photo data whether or not this is a banned photo? Using the information that we now know, we run our hash function on the photo, and that tells us where in the array to save a link to the image. The problem is that this isn't very space efficient. If we had just 1,000 images that were banned, and there are many, many more, and each took up a few megabytes, then already we'd be several gigabytes worse off, and certainly this wouldn't be something that we would hold in RAM. But recall that we're not actually interested in storing the images from our data structure, we just want to see whether or not it is in it. We want to be able to ban an image once, store the fact that this image is banned in an array, and then be able to quickly compare whether new images uploaded have a hash that is in the banned image array. So to try and tackle the space issue, instead of hashing an image and then storing a link to the image at the spot in the array dictated to us by the hash function, we can have the array contain a 0 at every index in that array. Then, if we want to ban an image, we hash it, then change that 0 to a 1 at the index in the array given to us by the hash function. So for any future images, all we need to do is hash it, and then we look at that index in the array. If it's a 0, then it's safe. We can be sure that we've never seen that image before. Certainly, we've never banned it. But collisions will occur, so images that are safe, some of them will be falsely labelled as banned. How can we stop collisions from happening in the first place? Well, we can't, but we can choose hash functions that have a vastly low probability of collision, such as the MD5 hash function. A new problem is that as the probability of collision decreases, the number of potential outputs increases, such that now for every 1 bit of output, we need an array of size 4 times 10 to the 25 terabytes, which we can all agree just isn't feasible to implement. So coming back to strategies for reducing collisions, we've already discussed increasing space, but there's another way. We can merely increase the number of hash functions that we use. In this new strategy, we don't just hash our image once, we hash it twice, using 2 different hash functions, and store a 1 at both positions in the array. Now, another image might have one of the hash functions collide with our banned image, but it's less likely that both hash functions collide. It's still possible, just less likely. If either position in the array for a newly uploaded image is a 0, then we know that we can't have banned this image before. And this is what a Bloom filter is. It's a field of bits, and the bits are set by different hash functions. Now, we don't have to stop at just 2 hash functions, we can go higher, 3, 4, 5, 10, 20 hash functions. And as we go up, the chances of collisions goes down. But there are some disadvantages though. Because we're using different hash functions and there is some overlap, we can put stuff into our Bloom filter, but we can never delete anything from it. Because there's some overlap, if we try to delete something from our Bloom filter, then we run the risk of accidentally deleting something else from the filter. What's more, even though we've reduced the chance of collisions, we haven't eliminated them, so there'll always be some chance of a false positive. But at least now, because we can control this probability, we can determine how much space and how many hash functions we need to include to have an acceptable solution. Bloom filters are really useful when you pair them with data structures that have worst case performance when looking for items that aren't there. So using the Bloom filter, you can answer very quickly that indeed the item that you're looking for isn't there, it's not in the data structure, so you don't need to bother to look for it, and that can save you a lot of time. I hope you enjoyed this short introduction to hash functions, hash tables, and Bloom filters. As ever, I look forward to your feedback, and I hope you enjoy the next tutorial. Take care now.